Okay, regression of the log wage. So when we have a actually we talk about it only the linear regression. So what we are doing is linear. So this side form is all linear. However, sometimes in many cases we will see the non-linear kind of relationship. So what we can do is simply the basic rule is we will transfer our variable into some nonlinear form, but we will handle that nonlinear form as a new variable. So if you apply the log onto the wage, and then you consider this is kind of a new y. Okay, and then if you change this to the new y, and then we are trying to explain new y using my x. Still now, after you change the y to the new y, now it's just linear again. So we can simply apply the same thing. What is the interpretation here, since it's a log, and then you can simply find out log of the wage, change of the log wage. So beta 1 is how much the education change increase by 1, how much the y value increase, right? So this is a log wages increase. So since this is yeah, you can consider this is kind of the like a derivative. So you can take a derivative of log wage. It's the 1 over wage times, no, this is like this is log, and wage, you take a derivative, then this is the wage over 1 times wage, d wage over dx, right? D education, actually. So do I have to do this instead of that, and then D education? Yeah, you know that the chain rule, you have to take a derivative of the big one and then multiply the derivative of the small one, the inside the function. So same way, and then you can just consider this is like instead of the previously, if you just use a wage, we trying to capture the how much education explain the wage, but now this is the how the increase of education will affect the percentage change of the wage, right? So interpretation is a little different, but actually you can simply change the value and then consider this is kind of new y, then you can simply has a mathematically same as a linear regression. Okay, so this is a semi-logarithm form because you apply the y side log, but you can apply the log to the other side. So this is how much education goes up, and then how much the percentage change on the wage. So as you can see, the wage and the education has a nonlinear relationship. So you can, if you use that, if you change this wage to the log wage, it will be more like a linear. Another case is what if we add the log here and log here, both sides, log and log. That's why it's a log and log form. Then, yeah, maybe you can get a better fitted line. And also the interpretation is the percentage change against the percentage change. And again, same way, you consider this is kind of a new y, and you consider this is like a new x, new variable. Okay, so don't think about this is like a log or something. You just created a new variable using the another variable. So originally there is a data x sales, and then you created a new column, and then you created a log sales. and then you consider this is x1, this is x2. Now instead of using x1, I will use x2. Then it's just simple linear regression. And then you can get a all linear regression coefficient. 0.257 means it's a 1% sales increase will generate the increase of 0.257% of the sales increase. And we will talk about the expected value of variance of the OLS estimator. So this is the how we already seen the how we calculate it, right? And then what will be the expected value of the estimator of the B0, beta 0 and beta 1 and variance of beta 0 and beta 1. So assumption of linear regression, simple linear regression is the first one is everything is a linear, right? This is a linear form. You cannot have a log or square, but again, we can consider x square as a put it into the like z, and then you can use a still linear function, right? This is a still linear form, but inside you know the z is actually the x square. So you consider the x square is kind of the another variable, then still you can use a linear regression. So that's why the linear regression is quite useful. Even though you have a non-linear relationship, you can handle, still you can handle, transfer the variable and then generate the new variable. You handle the variable is like a new variable, and then still you can handle it. Still you can create the statistical model. And then random sampling, because the we assume that our data is from the random sampling. So each data point is follow the population equation. So we don't know what will be the exactly the population model, but we can tell, since this is a random sampling, my estimator should be close to our population model. Just like calculating mean using the sample data, if the data is randomly selected, then we can estimate what will be the population mean. Now, this is just a procedure of the random sampling and wage. Population, all workers are of the country A. So we are talking about country A's all worker. Of course, you cannot examine everybody. In population there will be a linear relationship, right? In population there is a linear relationship. We cannot know, right? And years of the education. So we cannot know the whole population. So we just draw the random worker from the population and get information how much the wage and what is the years of education, and then you draw the worker back into the population and repeat the random draw again n times. So you are collecting n number of sample. And then using this n sample, we just trying to estimate the linear relationship here the population has. Obviously, our estimation will not be exactly the population relationship, but still we can estimate, just like a sample mean versus population mean. Okay, so random sampling. This should be the totally random. Otherwise, our estimation will not be close to the population regression model. Another assumption of the linear regression model here is the sample variation in the explanatory variable. This should be okay. This should be greater than 0. So this means is xi can we have a lot of different x value. If you have a what does it mean? This is a 0. No, you can, since this is square, it cannot be smaller than 0, but it can be very close to 0. What does it mean? It's very close to 0 is x, all x, x1, x2, x3, x4, all the x's are very close to x bar, which means you don't have a various x, you have a very close to the x bar number. So for example, let's say x bar is 5 and your number x1 is like a 4.9, x2 is like a 5.1, x3 is like a 4.95, x4 is 5.05, something like that. Every numbers are very close to 5, then this one will be very close to 0. It's not exactly 0. Then how can we predict anything? Because all the data you have is close to x equals 5. Then how can I get information what if x becomes 7? You don't have any data there. You cannot estimate even because you don't, all of the number you have is close to 5. Yeah, you can predict pretty close around 5, but what if x becomes 5, 7, 9? You cannot predict it, right? That's why your prediction power it depends on the how various x you have. And this should be 0, that we already seen this before. What does it mean? It says x should not be able to explain any u, right? So here the value of the explanatory variable must contain no information about mean of the unobserved factor. So they should not have any relationship. That's what it means. Zero conditional means. And unbiasedness of the OLS. This is the what does it mean is we find the here. So every time depends on the sample, we will have a different estimate of beta 0, right? So this is like that. One data set. Using this data set, first data set, you can estimate. We don't know what we will never know what is the beta 0, but we estimate it, and we also estimated beta 1, right? And second data set, right? We will estimate again. Yeah, you will have since this is different set, we will have a different number here, right? We will have a different number, and then you repeat it, you will get a all different number. But what will be the expected value, average of this number, if you do it enough number of time? That should be the real population beta 0. And if you calculate the average of all this estimate of the beta 1, expected value should be the real population beta 1. So this is what we call this unbiased. This beta 0 head is unbiased estimator of beta 0, population beta 0. Yeah, so see here there's a smaller or larger, so you can, it depends on the data, you have some small number, large number, right? But the average should be the population, right? However, on average, this is what I mean. So on average, they will be equal to the value of the population relationship true relationship in population, right? That's why this should be the average will be close to the real population. On average means if sampling was repeated, yeah, it's repeated, then the average will be the same as the population. Okay. Variance of the OLS estimator. So this is the what we talk about. So the question, the previous slide, what will be the expected value of the, right? So expected value of the, and the expected value of the beta 1, right? So we already answered the question. And then what about the variance of that? So variance will be calculated. So this variance, again, I should follow the normal distribution, 0 and the sigma square. So we don't know what is the sigma square, but this is the what we consider. Why this one has a just value? Because it doesn't depends on the xi. As x increase, if the variance is changed, that's what we don't see the homo here. Again, homo means this is the same. So everywhere the variance are the same. So you can see why is true, because the u should not have any information each other. X should not have any information on the u error. So everywhere, yeah, there will be a variance, but the size, the variance, size of variance is everywhere. It's not depends on the value of explanatory data. So X changes, but variance is still all same. That's why we call this is a homo. This is just the graphical demonstration of the hetero. Hetero means it's all different, right? So this is case. The variance is all depends on the what is the x. Depends on the x, you have all different variance here. So this is all different variance. That's why it's what we call is a heteroskedasticity. Yeah, again, it's hard to pronounce.